Good morning. I'm going to give you guys about 8 minutes to work through these, and then we will get started on them together. Good morning. I'm gonna break these down individually. So I'm gonna use some smaller paper or some new sheets. All right, let's start with this first one. Should get 4 products from this. Gonna make an enolate. With some extra stuff on it. We can add this in with itself. So our first product. Gonna have our enolate. Come down, attack this carbonyl. Eventually we're gonna come back down, kick out this OET here. So we're gonna form our starting material back. I'm going to draw it pointing down to make things a little bit easier. That's going to make a bond between this alpha position here and this carbonyl. We need the rest of our carbons on there. Should give us this final product. We could instead interact with our other ester here. Same concept. The only difference between these two reactions is I got a few more carbons over here, missing that isopropyl group here, so we should just get this chain on the end of our molecule. All right, other ester is going to make a different enolate. This can either attack the other ester or itself. So if it attacks the other ester, we are going to make something that looks very similar to this here, but now we have less carbons on our enolate instead of our ester here. So we're going to have less carbons in this position. So product should look like this. And then our final one, very similar, just removing those two. 3 carbons there. To give us this final product.
It's almost ready.
All right, let's move on to these. Either malonic ester synthesis or acetoacetic acid synthesis questions. So first one here, is a malonic acid synthesis question. We're going to throw in NaOET. Some sort of alkyl halide. Looks like it's this bromopropane. And then H3O plus neat. So first up, going to deprotonate at this alpha position in between these two esters here. Technically, make it enolate, but I'm just going to draw this resonance structure. Our electrons could attack this bromine here. We would initially make blue carbons coming off of this. And then in H3O plus and heat, we are going to lose these esters. They turn to carboxylic acids. And we're going to lose one of them and give us our carboxylic acid product. We could do this twice instead of, so this was a single addition. The next one, I'm going to go down and then over. So let's do the other malonic acid synthesis. So our first steps could be adding the same thing. All right, so these are the exact first two steps, same steps here. So we should end up with this compound. We're adding in another NaOET. You can pull this off, and then we can alkylate with another reagent. So I'm going to draw out that intermediate. Should look something like see, so we have 3 carbons here, and then 2 carbons in an iso. So we should get this here with H3O plus and heat. We're going to lose both of these esters to carboxylic acids. We are going to decarboxylate one of them to form our product. Question in the chat, which is, how do we know which side to become the carboxylic acid? It doesn't matter. So if for this first one, if you did the other one, put the OH over here. These are the same compounds. You just rotate it around this center. It's because it's malonate. You have, this is an entirely symmetrical molecule here. It's going to give you the same product no matter which one you deproton or which one you decarboxylate. So Typically I just always do the left one. So I don't know, makes it easier by just being consistent. All right, so this last one is a little different because we only have one ester and an acetone on the other side. So we only have one carboxylic acid for this one. So that's what's going to make this a little easier. We're going to have to deprotonate in the same spot. So let's kind of draw all these out. I'm going to do it in just kind of one big thing. So NaOET. We're doing, what are we adding? This bromide here. NaOET. Different bromide. H3O plus. So when I'm drawing these out, I tend to just kind of start with what I know is going to be my product. So I'm going to lose this whole group here and be left with just acetone. So I can start off by drawing acetone. And then I need to fill in both these alkylations. So I made a bond to where this Br is. So I need this isopropyl group. And then same thing here. And that can give you your product. It's kind of a quick way to think about these. If you're doing them on an exam and you want to not have to write out all your steps, you know you're going to lose this CO2 here eventually, which means you're going to be left with this skeleton, these 1, 2, 3 carbons, and then you're just filling in where your alkylations would be. All right, so today we are going to finish up 21. Wednesday we'll do some 22. It's a pretty quick chapter. You guys have already done, I think, every reaction in it. It's just amines, and we've already know how to make amines. So that'll go fast. When Friday we'll do some synthesis. Monday will be the exam review. Wednesday will be exam 4. Friday will be the final review. And then depending on which class you're in, you have a final on either Monday or Friday. So we're almost done. All right, let's talk a little bit about conjugate additions. Which we started to talk a little bit about on Friday. So if I take they call these alpha beta unsaturated, either ketones or aldehydes. It's a ketone. You don't really need to memorize that, but just so you know what I'm talking about. So this is going to be considered our alpha position here. This one here is going to be our beta position. So I may say alpha and beta a lot, and just so you know what I'm referring to. But for this first reaction, they're not going to involve these. If I take a Grignard in solution with one of these alpha beta unsaturated ketones, we are going to do our normal reaction. So attack your carbonyl. We'll end up making an alcohol. This other double bond can be untouched. We'll get this product. To do our actual alkylation at this beta center, because this is kind of just an extended ketone, You have another, if you attack here, your electrons flow to the same center just by 2 steps or 2 arrows instead of 1. So if I throw in our softer reagent, which is this lithium, copper, we made an ethyl group up here. Followed by H3O plus. It draws little quotations around it. So this like equivalent of ethyl minus. Can attack at this center here. We are going to do a 2-step version of this. So we'll kick the electrons over, and then we'll kick up to our carbonyl. Make an enolate. We're going to add H3O plus. So there's a lot of protons in solution. Pick up the proton. So reform your carbonyl. And form your product here. So it's kind of an extended addition. Instead of attacking at our actual carbonyl center, we're attacking at the end of the conjugation in order to do an addition there. So the actual Michael addition is the same reaction. We're just going to use a different, instead of a Grignard, we're going to use a diketone. So if I take this diketone here, I throw in, let's say NaOH. I can generate would be an enolate. I'm just going to draw this negative here. Technically, it's the enolate here and the enolate here. And then from this point, if I throw in that same Michael acceptor, so an alpha beta unsaturated, let's do an aldehyde this time. What I can do is I'll do an attack, just like I was doing at this beta position. Temporarily form an enolate. We add an H3O plus. To generate this tri-ketone here. On the page still. There we go. So something to note is that you're attacking at this position and not this position in the first class. And it's a little bit more prevalent on the when you do this on a ring. But and we'll go over that in a second here. There's just kind of this extra group floating off here, and that's just because we have an extra carbon here. So this is called the Michael addition. Let's do another example with a ring. We're going to see a lot of those when we start doing the Robinson annihilation at the end of this lecture today. So if I start with a cyclic diketone instead, same concept. We just now have a ring throwing in NaOH. Let's do this Michael acceptor, H3O plus. Oops. 3 H3O plus. There we go. Okay. So first we'll make negative charge here. Sorry, off the page. This can attack at our beta position. So we should have 1, 2, 3, 1, 2. Okay. Form the same enolate we've been forming. Adding in H plus. Our electrons can reform our carbonyl. Grab our H plus to give us our product here. All right, so something to note is that this does not work with just a single ketone. We're gonna have to do something different for that. So if I try to just take cyclohexanone, throw in NaOH, Michael acceptor, H3O plus. This is when it's going to give you no reaction. And it has a lot to do with the fact that because this is more acidic, it gives you a worse base. These ketones make a decent base when you actually form this negative charge here. So it's actually just going to pull off another proton. It's not going to act as a nucleophile like we want it to. So to get around it, we're going to use something called the Stork-enamine synthesis. I seem to have lost the first lecture for. Okay, so weird. Don't know where that slide went. Okay. What we're going to do instead is take our cyclohexanone here. We are going to throw in an enamine. So let's, I don't know, do a diethyl H plus here. The reaction from chapter 19, you guys should remember, we can form this enamine. And then from here, this is a pretty good nucleophile. So now we're to do the exact same reaction we just did. This would be step 1. 2 would be throwing in our Michael. acceptor. So we're going to have our electrons reform our imine, do an attack on this beta position here. And then the way we remove amines is the same way we protonate this. So adding in H3O plus is going to both give us back our ketone as well as our Michael product here. So this is called the Stork enamine synthesis. And you're essentially just using an enamine in order to do the normal Michael addition reaction. All right, we're going to talk about one more reaction today. It's called the Robinson annulation. It is a Michael addition followed by an aldol condensation. And it's probably the last real mechanism we're going to cover. 22 doesn't really have anything that's more than just like an SN2 reaction, so there's not much there in terms of mechanisms. So Robinson annulation. I'm going to write out one first, and then I'll write it out once, do the mechanism, and then kind of go through it again as a bit of a review. We're going to take a diketone, add in NaOH, our Michael acceptor, this is going to, whoops, not that. Have to be a ketone. It can't be an aldehyde. We'll talk about that in a minute. And then finally, more NaOH and heat. The NaOH is a little redundant because it's already in there, but you need the heat at least. All right, so our first step of this is going to give us, we're going to deprotonate, do the Michael addition. And then from here, we're going to do an aldol condensation. We're going to make an enolate here. This can either attack this carbonyl or this carbonyl. This one's symmetrical, so it doesn't matter. When that happens, so NaOH, I'm going to draw it attacking this one. So we would form a 1, 2, 3, 4, 5, 6 membered ring. With an OH, and then using heat, eliminate it to form a Robinson annulation product. So as I'm sure you can guess, this is going to be a pretty long mechanism. Give you guys a second to write that down because I think I wrote most of it off screen. so I'm about to go through every step of it. So if you're missing anything on this, we're going to cover it again anyways. So let's start with our diketone here. Got a proton on it. We're going to throw in NaOH, so OH minus. Pull off our proton, make an enolate. I'm just going to draw it as the negative being on this position, so I don't have to draw both those resonance structures. We can attack our Michael acceptor. So same reaction we've been doing. Let's see. We have water in solution because we made it in the first step. So we can reform this ketone. And that gave us NaOH. So we got the OH back. From here, we're doing our normal like ring forming concept. So if I was to pull off this proton here, I would make a 1, 2, 3, 4 membered ring, which is not really going to form. It's too hindered. Versus if I pull off this proton and make a 1, 2, 3, 4, 5, 6. Membered ring here. Those are really hard to read. 1, 2, 3, 4, 5, 6, which is a favorable ring formation. So because of that, the enolate I'm going to get has the negative there. We're just doing a normal aldol condensation. Let's see. Oh, shouldn't have drawn that up. Yeah. I'm just going to draw the O minus and then negative here. From this point, we'll do an attack on one of our 2 ketones. Pick those electrons up. It'll eventually grab the proton there, so we'll make I want more than that. This alcohol. So we made a bond between here and here, and we closed our ring. So that's our 6-membered ring here. Still have this methyl group, still have this methyl group, still have this ketone. This turns into an alcohol. And then from here, adding in heat lets us do, so we made OH, we can pull off the proton, make the double bond, kick this out and have it grab the other H to give us our final product here. All right, I'm gonna give you guys a minute to write that one down. And then we're gonna do one that's not symmetrical. If you're looking at it, it's just two reactions we've already done. This is your Michael product. Hey. All we did was pulled off a proton, did a Michael addition, formed this product here. And now all we're doing is an aldol. We'll pull off the proton. It'll do a ring closing one, eliminate the water, and get your product. So it is reactions we've already done before, but it looks a little scary because it's kind of a bunch of them at once. Yeah, so a methyl group. On to make this asymmetric. So first part's gonna be the same for both of these. We're gonna do our Michael addition. So we pull off this proton, attacked, came back down, reprotonated, finished our Michael addition here. From here, we're in NaOH again. We can make our enolate. And this can either attack the bottom ketone, so I'll do in red, will form initially an alcohol, which can go to product number one. Or in green, we can do the exact same reaction, but we're to attack the top ketone. Oh, I missed this methyl there, didn't I? There we go. Now we're forming the other alcohol. Which can then be eliminated to form our Robinson product here. And if it's easier for you to just draw this a little flipped around, you could also just like rotate the whole thing, and then this metal just shifts from here to here for your other product. Yeah, that's easier to think about. There's a question. Can you move the page up, please? All right, so this is the Robinson annulation. We'll do a couple more of these on Wednesday and cover a little bit of chapter 22, which is just a big review. And then I'll see you guys then. So have a great Monday.